So today we're going to solve simple exponential equations using common bases. So the first thing I want to talk about, which is up on the board, is our our bases. So we have 2 to the 1. First of all, let's start here. 2 to the 0 is 1. 2 to the 1 is 2. 2 squared is 4. 2 cubed is 8. And 2 to the 4th is 16. I kind of want to go up to all the way to 2 to the 5th. Let me do this. I did it again. One more time. Third time. 30 is a charm, right? There we go. So now I have 2 to the 5th is 32. We usually don't go any higher than 5. Right, Matthew? Do you remember what 2 to the negative 1 is? 1 over 2. What's 2 to the negative 2? 1 over 4. What's 2 to the negative 3? 1/8. They looked at me like I was crazy in the last period. 2 to the negative 4. 1/16. Because positive exponents make things get bigger exponentially, but negative exponents make things get smaller exponentially, right? So what would 2 to the negative 5 be? 1 over 32, right? Jay, put it away. All right, so we don't need that up here, but I am going to go through my 3's. So 3 to the 1 is 3. 3 squared is 9. 3 cubed is 27. 3 to the 4th is 81, and you might see 3 to the 5th, which is 243. 4 to the 1 is 4. 4 to the 2 is 16. 4 cubed is 64. I don't think you're going to see any numbers bigger than that for the 4's. And 5 to the 1 is 5. 5 squared is 25, and 5 cubed is 125. And I think we discussed you need to be comfortable with these. All right, you need to see a 32 and you're going to think what? 2. 64, 2 or 4, right? 125, you should be thinking 5. All right? Okay, that being said, now let's go to a recap on our graphing. So our most common base is 2. So we're going to talk about 2. I'm going to do 2 to the x over here. So here's my first function. 2 to the x. All right, so I've got my xy table. So first I want 2 to the 0. So if x is 0, then y is 1. If x is 1, y is 2. If x is 2, y is 4. If x was 3, y would be 8. If x was 4, y would be 16. Now, this is where we go in the negative. If x is negative 1, so negative 1, I get a half. 2 to the negative 2 equals a fourth. But of course, these numbers don't matter as much because we just know that they're getting smaller and smaller and smaller and smaller and smaller. It never crosses the x-axis. Because you could be 2 to the million, right? And it's still going to be a positive number. It's just going to be super small.
So that can go forever.
That can go forever. So the x-axis is an asymptote. So this is f of x. All right. Let's do g of x as 1/2 to the x. Now I say to myself, 1/2 to the x, when I see 1/2, I think 2, because it's the same graph, only reflected over the the y-axis. So I'm going to do the exact same thing. So if I have 2 to the 0, I'm going to have 1. If I have, sorry, it's not 2 to the 0, it's 1/2 to the 0. If I have 1/2 to the 1, I'm going to have 1/2. So over 1 is a half. 1/2 to the 2 is 1/4. So if I go over 2, I'm going to go up a fourth. Well, isn't that the exact mirror image of this side over here?
Yeah.
So when I think of 1/2 to the 1, I think of 2 to the 1. Sorry, thank you. 1/2 to the negative 1. Thank you. So 1/2 to the negative 1 is going to be 2. So negative 1, I go up 2. I'm going to explain it in a second, okay? Just let me get through it. And then 1/2 to the negative 2 is going to be 4. So negative 2, I go up 4. Negative 3, I go up 8. All right, so there's my g of x. Melody, you can't see with your eyes covered. Aylin, up here. All right. So when are exponential functions used in real life? We're going to talk about that more on Friday. Statistics, population, in science when we talk about half-life. Okay? All right. So we're going to solve exponential functions today. We're going to solve them graphically, and we're going to solve them algebraically. I'm going to show you graphically and algebraically side by side. Okay? We've done this before when solving equations in different functions by using a constant line and the graph. So on one side, if I have 2 to the x equals 8, I can write that as f of x is 2 to the x, and g of x, so f of x, changing my color, so f of x is 2 to the x, and g of x is 8. Remember how we've done that? We've split the equation into 2 different functions, and then we find where they intersect. So if I make g of x be 8, that's right here, they intersect right here, which just happens to be 3. Isn't 2 to the 3 8? Right? What about, we all know what 2 to what makes 4? 2. So the answer is going to be 2, right? Well, if I take my constant line and I go down to 4, isn't that intersecting at 2, where x equals 2? And if I bring my constant line down to this one, 2 to the 1 is 1. Sorry, 2 to the 0 is 1. If I bring my constant line down to 1, x equals 0. So that's another way to solve it. So we're going to do this graphically and algebraically side by side. So now I'm going to solve this algebraically. So I have my solution. My solution is 3. Right? Because this point is, when I go over 3, I go up 8, 3, 8. Well, x equals 3. All right, so this is how I'm going to solve it algebraically. Algebraically, I'm going to make common bases. That's the key. So 2 to the x, and I say, I know there's a 2 in there. The base in 8 is 2. So 2 cubed is the same thing as 8, correct?
Yeah.
So once I have common bases, I compare exponents. If the bases are equal, the exponents must be equal. Make sense? Recording once again. Alright, so 1/3. So I need to graph the function of 1/3. So f of x is going to be 1/3 to the x. This is where everybody got lost in, not everybody, I shouldn't say everybody. People got lost in 5th period because I started here. And they're like, what? It is, but we're going to, okay. So this is how I graph 1/3. I think of it as 3 to the x. Okay? So it's always, so 1/3, let's do it like this. 1/3, sorry, 3. 3 to the 0 is 1, right? So 3 to the 0 is 1. 3 to the 1 is 3. So I go over 1 up to 3, but it's on the other side. Right? Because isn't 1/3 falling? Remember? That's just how I do it. I think it's easier than thinking of 1/3 to the 1, then 1/3 to the 2, and 1/3 to the -1, right? Rather than doing that, which you can.
So 1/3 to the -1 would now be on this side?
It's here.
So what's 1/3 to the 1? What side is 1/3?
1/3 of the 1 is 1/3.
Oh, okay, that's okay.
And 1/3 to the 2 is 1/9. And 1/3 to the 3 is 1/27. Right? I'm thinking of it in terms of, I'd rather look at it like this. So 3 squared is 9. So I go over 2, up 9, but on the other side. Do I need to go back to my previous example? Yes. Yep. And if that's small, just estimate it. This is why I think of it that way, because of this right here. They're mirror images of each other, right? That's 2 to the x and 1/2. So when I want to graph something that's a fraction, in my mind, that's just me, I graph the one that I know, and then I put it on the other side. Does that make sense? Okay. Somehow I think I still have some of you are confused. Hold on, I'm almost there. Now I need to graph g of x, which is 3. I split them up. So 3 is here, and they intersect at -1. All right, now I'm going to do it algebraically. 1/3. I see 1/3 and I think to myself, that's really 3 to the -1. Would everybody agree that these two things are the same? 3 to the -1 is the same thing as 1/3, and 1/3 to the -1 is 3. And this is 3 to the 1. So this is really 3 to the -x equals 3 to the 1. Now I have common bases, and so now I can compare my exponents. So I have -x equals 1, so x must be -1. The beauty of this is you can always go back and check if you're right, right, Jonathan? How do I go back and check if I'm correct? Substitute it back in. So I substitute x equals -1 back in, 1/3 to the negative 1 must equal 3. Am I right? 3 equals 3. It checks. So that can always be done. Okay, ready for more step up? Okay, so now I'm just going to do these algebraically. So I'll start here. I have a negative 2 to the x. I can change negative 32. Remember I told you you're looking for bases. What's the base in 32? 2. Right? They're up on the board, the bases. Negative 2 to the 5th is the same thing as negative 32. Correct? So now that I have common bases, I can compare exponents. Once those bases match, the exponents have to be the same because there's an equal sign. So negative x equals 5, therefore x must equal negative 5. If I plug that back in or substitute it back in, negative 2 to the negative 5. Wait, this wasn't negative x. See how I checked? And I knew I was wrong? I couldn't have planned that one better. So negative 2 to the 5 is negative 32, so we're right. Let's do another one. They just look so excited to do this stuff. Like they just can't wait. This is 10 to the x plus 1. I know that there's also a 10 in there as well. Okay, if you get stuck here, don't second guess yourself. Go back and say 10 to the 1 is 10. 10 squared is 100, because 10 times 10 is 100. So 10 cubed is 1,000. So this is really 10 cubed. Common bases. Compare exponents. X plus 1 equals 3, so x must equal 2. 2 plus 1 is 3, and 10 cubed is 1,000, so we're right. One more step up, and then you guys are going to do this yourself. One more step up. You don't have to check. Sure. Yeah, if you're unsure, I would check it. So, what's my base in 9? 3. So 9 is really 3 squared. And 27 is really 3 cubed. Everybody okay with that so far? I have 2x, which is 4x. And I have 3 to the 3x minus 3. You got to distribute it to both. Common bases, compare exponents. So I'm left with 4x equals 3x minus 3. Take 3x from both sides and you get x equals negative 3. If x equaled negative 3, this would be 2 times negative 3, which is 6. Am I right? Negative 6. 9 to the negative 6 equals negative 3, 27 to the negative 4. Put them in a calculator, see if they equal. Right? Okay. 1/2 to the x. I can change 1/2 to 2. 2 to the what makes a half? Negative 1. 2 to the 5th is 32. So this is really 2 to the negative x equals 2 to the 5x plus 30. So now I've got common bases, so I can compare exponents. Negative x equals 5x plus 30. 0 equals 6x plus 30. Whoops. 6x equals negative 30, so x equals negative 5. You guys ready to dive into this?
Yeah.
You guys excited? You pumped?
Yeah.
All right, get pumped.